I'm just going to try to start the lecture now. So I'm making a recording of the lecture. The recording of the first lecture didn't work out, but I'll post the paper transcript. So I'm going to see if this one, I hope that this recording works out, and I'll be posting this as well and tell you where the recording is posted. And I'll also post the paper transcript. Okay, well, hope this goes well. Please bear with me. Every day it's a new crisis. Every day it's like a minute by minute change in whatever it is we're supposed to be doing. Okay, so today what we'd like to start out with is start to talk about the theme for the rest of the semester, which is the chemistry of the carbonyl group, of the carbon-oxygen double bond, which is the most important functional group in organic chemistry and also in biochemistry. So let's see. The chemistry of the carbonyl group. And remember, the carbonyl group is the carbon-oxygen double bond. That's what we see in aldehydes, ketones, carboxylic acids, esters, amides, all kinds of functional groups have the carbonyl group in it. All right, so that's going to be our topic pretty much for the rest of this unfortunate semester. Okay, so the most fundamental idea here is that the carbonyl carbon is an electrophile. All right, and what is an electrophile? An electrophile is a species that is electron poor. And because the carbonyl carbon is an electrophile, it's attacked by nucleophiles. And what's a nucleophile? Something that is electron rich. And I think possibly we talked about these at the last lecture, what some examples of electrophiles are and what some examples of nucleophiles are. So the carbonyl carbon is an electrophile and it's attacked by nucleophiles. We can see that the carbonyl carbon is an electrophile when we draw what is called its resonance structure. All right, so the carbonyl group has this carbon-oxygen double bond. And because oxygen is so much more electronegative than carbon is, oxygen is sucking electrons away from carbon. And we symbolize that with an arrow that looks like that. Okay, so this arrow means that oxygen is removing electron density. Oxygen is removing electrons from carbon. And we show that, and we use this double-headed arrow to show the result of this electron motion. All right, and so this is the resonance structure. It is simply saying that oxygen is sucking electron density away from carbon, and to such an extent that that carbon is now positively charged and that oxygen atom is negatively charged. Well, this makes sense because if oxygen is removing electrons, is sucking electrons away from carbon, most of the electrons are going to be near that oxygen atom, and that oxygen atom is going to turn out negative because electrons are negative. Another way of writing this, describing this relationship is to say that the carbonyl carbon has a partial positive charge, and that lowercase Greek letter delta means partial, and then that plus means positive. And the carbonyl oxygen has a partial negative charge. So this thing means partial positive charge, and this symbol means partial negative charge. And remember, we said that these guys were so-called resonance structures. They're simply indicating that oxygen is removing electron density from the carbon. Okay, so the carbonyl carbon is an electrophile. It is attacked by nucleophiles. And so a nucleophile is going to be something that's going to be electron rich. So this is a theme that we're going to keep emphasizing for the whole semester. It is the attack of nucleophiles on the carbonyl carbon. Okay, so now let's talk about how nucleophiles attack the carbonyl carbon. Okay, and this is called the way in which the nucleophiles attack the carbonyl carbon. This is called the Bürgi-Dunitz trajectory. Bürgi-Dunitz trajectory. And this is named for Bürgi was a Swiss guy, and Dunitz was a Scottish chemist, and they came up with this theoretical model sometime in the 1960s. And so what the Bürgi-Dunitz trajectory says is that nucleophiles attack the carbonyl carbon from above and below the plane of the carbonyl group and making a 109-degree angle with that plane and along, let's just say, and mostly along the path of least steric hindrance. Okay, so that's a lot. This Bürgi-Dunitz trajectory, that's a whole lot of stuff to digest, especially in this format. So let's explain with a picture exactly what this Bürgi-Dunitz trajectory is all about. Okay, so imagine the carbonyl group, right? The carbonyl carbon has a steric number of 3. The carbonyl carbon is trigonal and it's planar, which means that the carbonyl group can sit on a tabletop. So what I'm going to do is just represent this tabletop using dashing and wedging. So there's the carbonyl group. It's planar. It's sitting on a tabletop. So let me just write my little tabletop. All right, and so that's the plane of the carbonyl. The nucleophile attacks from above and below the plane of the carbonyl, and it makes a 109-degree angle with the carbonyl group. So what the Bürgi-Dunitz trajectory is saying is that the nucleophile, and so that's the nucleophile, I'm going to put a negative charge on him because remember, a nucleophile is something that is electron rich. He's attacking the carbonyl carbon from above the plane and making an angle of about 109 degrees. So this angle, the angle that the nucleophile carbonyl carbon and carbonyl oxygen is making, that's the angle that is about 109 degrees. But the nucleophile can also attack from below the plane of the carbonyl. So that's the other option, where the nucleophile could be down here somewhere, and it will come in attacking the carbonyl carbon once again from below the plane of the carbonyl, and here making that 109-degree angle there. All right, so that's the Bjerke-Dunitz trajectory. The only thing that is really left to explain is why this happens, and also what we mean by the path of least steric resistance. Well, maybe in Gen Chem, maybe you heard about orbitals, maybe you've heard about the pi orbital. Well, the nucleophile is attacking the carbonyl carbon because this is where the pi orbitals of the carbonyl group is. Okay, so I'm going to redraw this picture somewhat. And this time, instead of writing those bonds, what I want to emphasize now is the orbitals that are involved in this interaction. So you have the carbonyl group here, right? And it has an orbital that is pointing in this direction. It has an orbital that's pointing in this direction. Orbital there, orbital there. So what are these? This shows the orbitals. And the nucleophile, he also has an orbital. And so the nucleophile's orbital wants to interact with the carbonyl orbital, but because the carbonyl orbitals are 109 degrees, 109 degrees relative to this plane, that's why the nucleophile comes in along this trajectory. So there's the nucleophile orbital, and he wants to interact with the orbital on the carbonyl carbon. And here he's attacking from above. And then we also have a nucleophile could be down there. And that circle represents his orbital, and he wants to interact with the orbital that is in the bottom of this plane. So this is this orbital explanation, which is pretty advanced. This explains why it is that the nucleophile comes in from above and below the plane. And it also explains why it makes this 109-degree angle, because that's where the orbital of the carbonyl group is. Okay, now let's talk about attack along, what we mean by attack along the path of least steric resistance. Some carbonyls, the carbonyl carbon in some compounds doesn't have a more hindered side or a less hindered side. There aren't any groups, methyl groups, or anything else sticking up in the way of the carbon, in the way of the entering nucleophile. So an example would be something like acetone or propan-2-O. And once again, maybe we can draw this little tabletop, and let's put the carbonyl group sitting on top of this, this tabletop. And over here, I'm going to put a CH3. And over here, I'm going to put a CH3. And what I'm trying to show here is that the nucleophile, which is going to come in from above and below the plane, it isn't facing, it doesn't have to get by, it doesn't have to face big, bulky groups as it approaches from the top or from the bottom. So the nucleophile can come in along this trajectory. It can also come in along this trajectory, but neither face That's an important vocabulary word here. Neither face of this carbonyl is more hindered than the other. So what I'm showing here is both faces, both carbonyl faces are equally hindered or not. So a concrete example would be, so let's straighten this up, same as we have the carbonyl group here, CH3 over here, CH3 over here, and now let's attack this with a nucleophile, something that is electron rich, maybe something like the cyanide ion, right? Cyanide, that's a nucleophile. That carbon has a negative charge. And this cyanide can attack the carbonyl from the top and from the bottom of this imaginary plane with equal probability, so that we can represent it this way. The nucleophile attacks the carbonyl carbon. Okay, so that should make a whole lot of sense because the carbonyl carbon is an electrophile. Cyanide ion is a nucleophile. So here we're showing the cyanide ion attacking the carbonyl carbon, but we can't stop there because if we were to stop here, that carbonyl carbon would have 5 bonds. So as the nucleophile comes in, as the nucleophile makes a new bond to the carbonyl carbon, the carbonyl oxygen bond has to snap, because if we don't snap it, we're going to get a carbon atom with 5 bonds. So that would be represented by this curved arrow. And remember at our previous lecture, if you were able to attend, we said that these arrows represent the motion of electrons. Okay, so the nucleophile has come in. Let's say it came in from the top. Because I straightened this picture up, that's equivalent to saying the nucleophile is coming in from the front. And so we would represent the CN on a wedge. And that what used to be the carbonyl oxygen got flipped to the back, but now it must have a negative charge, because when oxygen forms one bond, it has a negative charge. Remember that from the first lecture of the semester. Okay, and so that would be the product that we would get, but we would also get another product, which would be the result of the attack of the nucleophile from the bottom. And since I straightened this up, the bottom is now going to correspond to the back. So the other product that we would get here would be, again, we need a dash and we need a wedge, but now the nucleophile has come in from the back. It's going to be on a dash, and the carbon, what used to be the carbonyl oxygen, got shifted to the front, and so that's going to be on a wedge. So we can label this as attack from the top. This would be the same as attack from the front. And this is the result of attack from the bottom, but this is equivalent to attack from the back, right? So I hope that you can see that there's a correspondence between the attack from the top and the bottom and the front and the back. So, okay. But now when we look at these two structures, we see they are identical structures. They are superimposable mirror images of each other, and that's our definition for identical structures. So these two things are identical, right? This isn't a chirality center. That's not a chirality center. There's no R and S. These are not enantiomers. So in this situation has given us the very same compound. Okay, so let's do another example. Let's dispense with that plane. And now let's work another example where we're trying to reinforce this. All right, so here we have this thing called acetophenone. And we're looking at this molecule, and the first thing that we're doing is we're asking ourselves, does this molecule have a more hindered carbonyl face, and does it have a less hindered carbonyl face? In other words, is the approach of the nucleophile from the front as easy as approach of the nucleophile from the back? And so we would conclude here that it is, because there's nothing on a wedge that is sticking up in the front that is going to impede or hinder the approach of the nucleophile from the front. There's nothing pointing back on a dash that is going to impede or hinder the approach or entry of the nucleophile from the back. So this guy has both faces are of equal approach. So once again, when we react this with a nucleophile, all right, let's switch up the nucleophile. Let's put in, a nucleophile is something that's electron rich. Maybe let's put in OH minus. The OH minus, its electrons are going to come in. The nucleophile is attacking the electrophile. We can't stop there, because if we stop there, we're going to have a carbon with 5 bonds. So as the nucleophile comes in, the double bond to carbonyl oxygen must break. Remember, these arrows represent the motion of electrons. They don't represent the motion of atoms. And so here what we're going to get is we're going to get one product in which the OH minus came in from the front, and we're going to get another product in which the OH minus has come in from the back, to give something like that. And so now, are these identical structures? Oh, they're not. They're enantiomers. Because what I've done here is I've created a new chirality center. One of these is R and one of these is S. So these guys here, they are enantiomers. This guy here would be, let's see, this is going to be the winning group here. This methyl group is the loser. So this is the 1, 2, 3. That's the S absolute configuration, and that's the R absolute configuration. Okay, so this case is different from the one we just did, because here enantiomers were created. This new chirality center was created. And because the nucleophile can come in from the front or come in from the back with equal probability, what we're going to get is 50% of the product mixture is going to be the S enantiomer, and 50% of the product mixture is going to be the R enantiomer. So, so we see that we can get a single compound where no new chirality center was created, or we can get 2 enantiomers, right? And this this may or may not be a disaster in the laboratory, because remember earlier in the semester, we talked about how when you ingest 2 enantiomers as a drug or whatever it is, those 2 enantiomers have different properties inside your body, because enantiomers have different chemical properties when they interact with other chemical substances, and all of the enzymes that control all of your metabolic functions, they are all chiral. So here, this is an example in which we get enantiomers. All right, so now let's look at yet another example where we're trying to show that the nucleophile is going to come in along the path of least steric resistance along the Bürgi-Dunnes trajectory. Okay, so for that, probably what we would want to do is look at a witch's hat type of molecule. Oh, I love this thing. right, and what I'm going to do is I'm going to put the carbonyl here, and I'm going to put two big bad methyl groups there. And now I'm going to feed this a nucleophile. I'm going to feed this, let's see, maybe the CH3 minus. That's a nucleophile. How do I know it's a nucleophile? Well, it's electron rich. It has that negative charge on it. And now this nucleophile is going to attack the carbonyl carbon from above and below the plane and making that 109-degree angle of the Bjerg-Dunitz trajectory. But here we see that for this nucleophile to come in from the top, oh, it has to get by this methyl group that's in the way. Attack of this nucleophile from the top is much harder than attack of the nucleophile from the bottom. So attack from the top and from the bottom both happen, but it's just overwhelmingly easier for this nucleophile to come in from the bottom. So in this case, what we're going to get is a major product and a minor product. We're not going to get a 50-50 mixture of two products. We're going to get a major product and a minor product. The major product is going to be the result of attack from the bottom. And again, this carbonyl bond has to snap. Product here is going to look like this, where the CH3 came in from the bottom and that carbonyl oxygen got flipped to the top here. This is the major product because it's why? Because the nucleophile attacks along the path of least steric resistance. All right, we could also identify the minor product. All right, so let's just redraw this. Looking like that. And there's the nucleophile CH3 minus, and this is going to come in from the top like this. And the product here would show that methyl group, that entering methyl group is now on the top, and that O minus went down to the bottom. This is the minor product because the nucleophile here has come in along the path of more steric resistance. And how are these two related? Are they identical structures? Oh my heavens, no. One of them has that new methyl group pointing down, the other one doesn't. So they're not identical structures. Are they enantiomers? No, they're not enantiomers either because there's no, enantiomers are non-superimposable mirror images. There is no mirror that is going to flip that downward pointing methyl to an upward pointing position. So these guys, these two products here, these are diastereomers. They're diastereomers. And if we remember what the definition of diastereomer was, they have totally different properties under all conditions. Okay, so we see that the attack of a nucleophile on the carbonyl carbon can lead to a single compound, to enantiomers, and to diastereomers. So let's just try to reinforce this concept. Let's just do some problems and look at some specific examples. All right, so maybe something like this. Cyclohexanone. And now let's react that with a nucleophile, maybe methoxide, OCH3 minus. Yeah, that's a nucleophile. So what about this? Is this going to lead to a single, let's predict the product, and then let's also predict whether it's going to be a single compound, two enantiomers, or two diastereomers. Okay, so you'll be working on that, right? Draw the structure of the product and tell me whether you get a single compound, a mixture of two enantiomers, or a mixture of two diastereomers. Do I dare click this chat to see what people are talking about? Okay, so I see that people are, all right, so I see that people are asking where you can find the record. Please bear with me, right? This is all new. This is all new to me. The lecture on Monday, that the recording did not work out. It was not of any, it was not of high enough quality for me to post that anywhere. So I'm going to post the paper transcript. I'm hoping to get better, right? All of the, another thing that has happened here on campus is that they've closed down all of the buildings, right? I'm just looking around for a classroom to try to give these lectures in. All of the buildings are closed. The classrooms are closed. I just happened to stumble into this classroom now. So, every day it's 5 or 6 crises. So I haven't had a chance to upload the record. I'm hoping to get better. Please bear with me. Okay, so what is happening here is that if we look at this carbonyl, is the front harder to approach than the back? No, the front and the back are equally hindered or equally not hindered, however you want to describe it. So the nucleophile is going to come in from the back and from the front with equal probability. So if we wanted to draw the two products, what we would get is, there's the nucleophile attacking the carbonyl group. The nucleophile 50% of the time comes in from the back, and 50% of the time comes in from the front. Okay, so that would be the result of attack from the front and from the back. And we see that these are equally probable. And now we have to look at these two structures and decide, are they identical? Are they enantiomers, or are they diastereomers? Well, the easiest way to solve this problem is to ask yourself, has a new chirality center been created? So is this a chirality center? No, because this road is the same as this road. Is this a chirality center? No, because this road is the same as this road. So no new chirality center has been created. Therefore, these guys are identical structures. So we get one and only one product. We get a single product. So how did that go? Did you try that? Did you come up with that answer? Hope so. Okay, so let's see. Does this do anything? Does this do anything? No. Yeah, this place is not set up for distance learning. Okay, so let's try another one. What about if we have a let's have a carbonyl carbonyl group here, and maybe let's, on this side, let's put cyclohexane, and there's our carbonyl, and on the other side let's put a benzene ring. All right, and now let's feed this in nucleophile, maybe Cn minus. Okay, and so now the question I'm asking you is draw the structure of the product or the products, include dashing and wedging, and then tell me whether those products are identical structures. In other words, we got a single compound, or whether they are enantiomers or whether they are diastereomers. So once again, we ask ourselves, is it easier for the nucleophile to come in from the back or from the front, or is attack of the nucleophile from the front or in the back equally easy? Well, this carbonyl, okay, so you think about that for a second. So this carbonyl doesn't have a more hindered side or a less hindered side. It's equally easy to approach from the front and from the back. So we can draw the products with that in mind. 50% of the time, the nucleophile is going to come in from the front. So I'm going to put CN here on a wedge and O minus here in the back. And 50% of the time, the nucleophile is going to come in from the back. And so for that one, I'll put the nucleophile on a wedge. I'll put the nucleophile on a dash and that oxygen atom on a wedge. And so representing this with arrows, the nucleophile attack the carbonyl carbon and snap that carbon-oxygen double bond. Okay, and so those would be the two products. And so what we see is we get 50% of that and 50% of this. But now we have to ask ourselves, are those identical structures? Are they enantiomers or are they diastereomers? Well, the simplest way of solving that problem is to ask ourselves, has a new chirality center been created? And it has. This is a steric number of 4 carbon that is bonded to 4 non-equivalent groups. So we have 2 chirality centers. We have a new chirality center here. One of them is going to be R and one of them is going to be S. Okay, so let me see what's going to, oxygen's going to win, and then nitrogen's going to be 2, and this cyclohexyl is going to be the lowest rank, so it's going to be 1, 2, 3, this is S, and this is R. Okay, so a new chirality center was created, so this is going to give 2 enantiomers as the product, right? So when the nucleophile attacks, you could get a single compound, you could get enantiomers, or you could also get diastereomers. Okay, so let's look at a 3D drawing, and you can bet that this is going to give diastereomers. So maybe something that looks like that. And now what I'm going to do is I'm going to put this big bad group up here, and I'm going to put the carbonyl there. All right, and now the nucleophile, let's let this nucleophile be CH3 minus, let that be the nucleophile. And now once again, draw the major product, predict the products, right? There will be 2 of them, one with approach from the top, one with approach from the bottom. And then look at the structures and tell me whether there's identical structures, enantiomers, or diastereomers. Okay, so hope you can see that the approach of the nucleophile from the top is going to be much more difficult than approach of the nucleophile from the bottom. Because if the nucleophile tries to get in from the top, it has to skirt its way past this stick-up feature here, and that is the path of greater steric hindrance, approach from the top. So approach from the bottom is going to be easier. Okay, and so the products here is going to be, we're going to have a major product and we're going to have a minor product. So the major product is going to be the result of attack of the nucleophile from the bottom, right? That's going to be major. Approach of the nucleophile from the top, that's going to be minor. And so the nucleophile came in from the bottom. It flipped that O minus up. And so this would be the major product. Approach from the bottom. And notice I didn't write this methyl group pointing straight down because we have to remember that this carbon here, it's a steric number of 4 carbon. It has to be a chicken foot, right? So it can't be this O minus is sticking straight up and this methyl group is sticking straight down because that would not be that characteristic tetrahedral shape of a chicken foot. The minor product is going to be the result of attack of the nucleophile from the top. So looking something like this, there, that nucleophile came in from the top and that O minus got shoved down like that. This would be the minor product. Okay, and so we get 2 different products. How are they related? Well, are they identical structures? Oh, heavens no. One of them has the O minus pointing up. The other one doesn't. Are they enantiomers? Are they non-superimposable mirror images? No, once again, they aren't because there's no mirror that is going to make that stick up O minus the mirror image of something that doesn't have a stick up O minus. So these guys are diastereomers. Okay, so these are just some examples of an application of the Bürgi-Dunitz trajectory and what we mean by by that term. Okay, so now we know how nucleophiles attack the carbonyl carbons. Now let's talk about trends in carbonyl reactivity, because it turns out that not all carbonyl compounds are equally reactive. Some react with nucleophiles to give 100% yield of product very quickly. Some carbonyl compounds react with nucleophiles